Let's focus our attention on isothermal reactor design, especially for CSTRs. Let's consider the CSTR for liquid phase reaction, where typically we get information about the initial and the final conditions in the reactor. From the mole balance, we can get that the volume of the CSTR can be expressed as a relationship of the initial flow rate over the rate of reaction. Remember that for a CSTR, we're always assuming that it is the exit stream, right, is operating at the rate in the inside. So besides knowing the volume of the reactor, we are also very interested to get the characteristic time, tau, that we discussed before as a function of conversion. So let's work out some definitions for this variable tau. So given that the flow rate initially can be defined as the volumetric flow rate times the initial concentration, we can come up with a definition of the CSTR volume. Okay, so now let's consider a single CSTR with the first and second order reactions to see the relationship between conversion and tau, the characteristic time tau. So let's start deriving or coming up with an expression for a first order reaction. So there's a couple of steps, right, that we are using not to memorize the information, and this is the chemical reaction engineering methodology. And always we define the limiting reactant, and when we know that, we start working or figuring out the design equation, which we already did, and then we define what is going to be the rate law for the reaction that will be in the reactor. And then we know from the statement, right, that we are considering a reaction where the reactants are in liquid phase. Therefore, V0 equals to V, right, for liquid phase. We're assuming that. So from the stoichiometry, we can get right, that the concentration at the exit of the reactor can be defined as fallow, right, in terms of conversion. So if we combine this information to get tau, remember that tau, right, is defined as the volume over the volumetric flow rate equals to Ca0 concentration over K, Ca0 1 minus X. Okay, so we can then define tau as 1 over K X 1 minus X, right? If we rearrange this, okay, to get the concentration, the conversion, we get that the conversion equals to tau times the specific rate 1 plus tau, this specific rate. If we do a graph, right, if we try to understand this behavior, we can get that, right, the conversion profile equals, right, or will have this form where tau and this here have multiplied by the specific rate. So there are a few comments, right, from this derivation. I want you to look at the analytical solution and the graph, and from that we can say, right, that at large tau k values, we produce or we have higher conversions. However, if we look from the graph also, this effect, right, is less significant, or I'm sorry, is more significant at lower values, because if you look at the graph here, you see bigger changes. So the reality is that if we change X in this region, the effect on the conversion will be really small. So in conclusion, we can say, or we can notice, right, from the graph and all that, that if we have higher temperature, right, we know that the specific rate increases exponentially. Therefore, the tau k value increases too. In the other case where we increase the volume of the reaction, we are decreasing, right, the volumeric flow rate of the reaction, then we notice, because of the definition of tau, that tau will be decreasing. Therefore, okay, tau will be increasing here. There you go. Therefore, this also affects or makes the term tau k increase. I mean, this is just a summary, but this is something that we can clearly observe, right, from the graph or the analytical solution for this particular example. So I just want to mention as a last note that with this information, we can also define the concentration in the exit, right, in terms of tau. So that means that we can have a concentration profile that actually it is related to the characteristic time inside the reactor. So let's use now the example where we have a second order reaction in a CSTR, and we're going to use this example to introduce a dimensionless number, just like the Reynolds number that is really common in chemical engineering, that is called the Damkohler number. So the Damkohler number or numbers are dimensionless numbers used in chemical engineering to basically relate the chemical reaction timescale, which is the reaction rate concept, with the transport phenomena occurring in a system. So, we can use it in different areas in chemical engineering. Typically, what we're trying to relate in a Damkohler number is pretty much the reaction rate with the convective mass transport rate. In our case, we're going to use the tau as the characteristic time as one of the properties that will be used to define this Damkohler number. So let's consider again the second order reaction in a CSTR. I'm not going to go through all the chemical reaction engineering methodology, but remember that we always, state the mole design equation for the reactor that we're talking about. Then we talk about the rate law, and we identify any assumptions that we can make in the volume, if it's a gas phase or liquid phase reaction. Then once you have that, you combine that information to actually get the design equation in terms of conversion for that particular reactor. So in this particular case, we can get, right, that the volume of a CSTR, right, considering secondary reaction, can be defined as follows. Okay, so if we do the stoichiometric table, we can get, right, information about the concentration at the end. which is very important for our definition on the rate. Remember that there's some assumptions that you have to make. For example, that the volumetric flow rate, right, is constant. There's no change in density. Also, that we can get from the stoichiometric table, right, that the concentration at the end equals to this. If we and we can also define that the flow rate, right, entering the reactor, okay, can be equal to the volumetric flow rate, right, of CA0 times X. If we combine that information, we get that the volume 1 minus X. Okay. So you can go and practice your step and try to see if you can come up with this design equation. Remember that at this point you should know how to do this. We have practiced this many times. So what I want to do right now is to focus on getting conversion in terms of the characteristic time, tau, because that is going to give us this new definition of the Damkohler number that we can use it to characterize, right, the relationship between the reaction rate or the chemical reaction time scale with the transport phenomena, right, or the convective mass transport rate. Dividing by the volumetric flow rate, the above equation, we can get, right, the characteristic time. Here we have a relationship between tau and the conversion. However, we have to simplify this equation and solve for x. I'm not going to do the math, right? This is a simple algebra. You have to be, solving this equation in terms of tau for conversion. So the final solution or the final expression for the relationship between conversion and tau ends up being something like this. So we end up having an expression similar to this. I recommend you, if you want to take the time to write down all this, to pause it. I'm going to continue for the sake of time. I want you to notice that there's like a common term, right, that repeats in that final solution. This is the term called the Damkohler number for a second order reaction. So the subscript there that you see here, right, is just indicating the second order, right, where this definition came from. The other thing that I want you to notice here, okay, is the minus sign that the solution that we got, right, from the quadratic formula. This sign must be chosen in the quadratic equation because the x cannot be greater than 1. Okay, so remember that we need to make sure that the maximum conversion that we can have for our irreversible reaction is 1. If we are in equilibrium, right, that number may be less than. So what we're going to do now is that we're going to plot this relationship so you can have a feeling of the relationship of conversion versus as a function, right, of the Damkohler number for a second order reaction. Before that, there are two factors that may affect the relationship of tau times k, right? Or in this case, it's the Damkohler number because the initial concentration is just constant. So we mentioned that we can increase the temperature, or that will be affecting k, or we can increase the volume, which will decrease the volumetric flow rate, therefore increasing the Damkohler number. Previously, we also noticed this, that in reality that we may increase tau, but the reality is that the conversion may not change a lot at higher Damkohler numbers. So I want you to look at the Damkohler number of 6. So we're looking at this, right? And then if we do an increase of tenfold, right? This is pretty much on a scale of 10, right? Tenfold. We notice that there's not like a very significant increase on the conversion, even that we are increasing the Damkohler number, or it could be the reactor, it could be the temperature, whatever we're doing at higher conversions doesn't really affect that much. So remember that CSTRs have the very special characteristics that they are operating, the conversion that we calculate is operating at the lowest conversion or the lowest condition, right? Or the lowest concentration of reactants in the reactor. So CSTRs are very useful, and the algebra is pretty simple, but sometimes we may have some limitations, right, at different experimental ranges, and this is one of the cases. It's pretty much because the CSTR is operating under the conditions of the lowest reactant concentration, and therefore it is just the smallest value of the rate of reaction. So anyways, this is an overview of the reactor of the Damkohler number, right, and how we calculate. But I want to now dedicate a little bit of time understanding what is the meaning, right, physically of the Damkohler number. This number is really important in chemical engineering. It's just like the Reynolds number, which is a very, very classic unitless number. So let's spend some time understanding this concept. Let's talk a little bit about the Damkohler number. As I mentioned before, it's a unitless number, and it's very, really important in chemical engineering. It actually gives us a quick way to estimate the degree of conversion for a continuous flow reaction. Typically, it relates the rate of reactant at the entrance and the entering flow rate. We can get expressions for different type of orders of reaction. I'm gonna just show you the first order and second order, and then we're gonna compare conditions where the Damkohler number may be affected the conversion. First order reaction, we have that the Damkohler number. Okay, here the subscript is telling me the order of the reaction equals to K1 Ca0 V over the volumetric flow rate. Okay. So if we group together, right, the variables, we end up having here Ca0 cancels. We end up having the Damkohler number equals to this. For a second order reaction, as we mentioned before, right, we did it with the previous example, we can get that equals to tau K2 Ca0. Okay. So with this, we have the definition for the Damkohler for this for two type of orders of reaction. So we use these numbers to characterize or to estimate the flow reactors, especially the CSTR. If we consider as not irreversible reaction, we can come up with some rule, like a rule of thumb, if you say. We can find that if the Damkohler number is less than 0.1, then the conversion will be less than 0.1. And if we get that the Damkohler number is larger than 10, then the conversion will be 0.9. And I mean, this is for an irreversible reaction, knowing that the maximum conversion for that reaction is close to 1.